One of the major drawbacks of living in a tropical city is summertime. It's damn hot. How hot? Well, with the help of a little chip, a dodgy power supply and a multimeter, we can figure out exactly how hot it is. So with a single 3-pin chip, I can read the voltage and convert it directly to temperature. In this case, 45.3 degrees Celsius, which is 113.5 degrees Fahrenheit. This little chip's really easy to use in any analog measurement circuitry. In this case, pictured here is a thermostat application which switches a fan on and off in a certain temperature range. We'll look at this circuit in more detail shortly. According to the data sheet, the LM35 has a very good accuracy, 0.5 degrees Celsius at room temperature, and it has excellent linearity over its range. As I mentioned, the LM35 is calibrated in degrees Celsius, but for our American friends, the LM34 is calibrated in degrees Fahrenheit. For ease of use, the output is calibrated directly to degrees, divided by 100. So 20 degrees Celsius is equal to 0.2 volts or 200 millivolts. 32 degrees, 320 millivolts. So very easy to use in a circuit. Making it very easy to use is its supply voltage range, all the way from 4 volts to 30 volts DC. In this application, I'm using the LM35 as a thermostat in order to switch a fan on and off at a certain range of temperatures. You can see on the multimeter we're reading 325 millivolts, which is equal to 32.5 degrees Celsius, or 90 degrees Fahrenheit. In this arrangement, we have a fan, 24 volts DC, connected to the controller board here, and we also have the LM35 connected as the temperature sensor. The multimeter on the left here is reading the voltage directly off the LM35, and in this case it's showing 32.7 degrees Celsius. The role of this system was originally to ventilate a computer that was mounted under my desk. The schematic for the system is shown here. It uses an LM324 quad op amp. The temperature is sensed by the LM35, shown on the left. The temperature reference setting for switching the fan on and off is shown on the non-inverting input of the op amp. And the hysteresis, or the deadband setting, is set by the 560k resistor connected between the output and the non-inverting input. The role of this resistor is to feed back from the output back to the non-inverting input, so that when the output state changes, so does the reference voltage. This prevents any rapid switching and produces a clean switched output. On the right hand side we have another op amp connected in inverter configuration, and this drives the FET, which in turn switches the fan and the red LED on and off. This is a brief demonstration of the thermostat in action. I'll warm the sensor up using my hand. You can see the voltage on the multimeter there corresponds to the temperature divided by 100, so 34.9, 35.1, etc. degrees Celsius. And the fan switches on when the voltage from the temperature sensor reaches the reference voltage on the non-inverting input of the op amp. Now for the reverse process, as the sensor cools down, the voltage drops below the reference voltage on the non-inverting input and the fan switches off. So we can see that the fan switches on at 35.1 degrees Celsius or 95.4 degrees Fahrenheit, and switches off again at 31.8 degrees Celsius or 89.2 degrees Fahrenheit. Taking a closer look at the hysteresis, or the setting of the deadband, On the left hand side here, we can see a slightly redrawn circuit. The actual circuit has a potentiometer by which we can set the reference voltage. It is actually set so that on one side the overall resistance is 71,000 ohms, and on the grounded side it's 1915 ohms. As described earlier, the hysteresis resistor, the feedback resistor, is connected from the output of the op-amp to the non-inverting input. So what we can see here is that as the temperature increases above the reference voltage, the output will go in close to 0 volts, effectively grounding this end of the 560k resistor. And this basically puts it in parallel with this resistor here, drawing this reference voltage down slightly. Conversely, as the temperature voltage drops below the reference voltage, the output goes positive. When the output voltage goes positive, we can think of this as placing this end of the resistor at roughly 12 volts. And in this case, it places this resistor in parallel with this resistor, pulling up on this reference voltage slightly. So by changing this reference voltage each time this state changes, we're pulling the reference voltage away from the current temperature voltage, and that way we can avoid any nuisance switching. If we consider this situation again, the temperature voltage being lower than the reference voltage, in that case the output of the amplifier is high, effectively putting these two resistors in parallel, and through Ohm's law we can calculate the reference voltage is now 0.36 volts. So again, the temperature is lower than the reference voltage. The temperature has to increase and increase and increase until it gets to this point. When it does, the output of the op-amp goes negative, and we can see here it switches this resistor in parallel with this lower one here. Now the reference voltage has dropped to 0.32 volts. So that defines the lower edge of our dead band. Now the temperature voltage has to drop to this voltage. When it does, the reference voltage flicks back to the top end of the dead band, and the cycle starts again. Indeed, a handy little chip, especially for any simple analog applications you have where you need to switch temperature or even measure temperature. Well, that's all for today's video. I hope you enjoyed it. If you did, give it a thumbs up. If you have any questions or comments, please leave them in the comment section below. Thanks for watching, and have a terrific day.